Hi. In the previous session, the last thing that we talked about was Markov decision process, Markov states, and we talked a lot about the states and the implications of choosing a state representation. In this lecture, we are going to talk about Markov decision processes. We are going to see what is a Markov decision process, and we are going to use Markov decision. We are going to see how we can solve Markov decision processes. Let's uh, you know dive in. So, as we mentioned briefly in the previous session, a Markov decision process uh, is a mechanism, is a uh, uh, tool for describing an environment for reinforcement learning. So we use Markov decision processes to describe environments that we are going to use those environments for reinforcement learning. And when we use Markov decision processes, we assume that our environment is fully observable. So the current state of the our problem is completely characterized by uh, characterizes the process. So uh, so when you know uh, your state, that's the only thing that you are going to need to predict the behavior of the environment, um, independent of the past states that you have seen. Uh, as you see here, almost all of the RL problems can be formalized as MDPs. So we are going to see a lot of problems, and we are going to convert those problems into MDPs. Even when you have partially observable environments, again you can convert them to MDPs. If you recall from our previous session, uh, we talked about that uh, we talked about Markov property, and we said that a state SD is Markov if only and if the probability of the next state given the current state is the same as the probability of the next state given all of the previous states. So your state, in other words, we talked about that your state has all of the relevant information that you are going to need to predict the behavior of the environment based on the current state. So again, I'm emphasizing that if you have the current state, you wouldn't need all of the history that you have seen, all of the states that you have seen in the previous states. So once the state is known, the history may be thrown away. So you don't need history when you have your state. Or in other words, the state is a sufficient statistic of the future. So again, as you saw in the previous session, when you have the current state, when you have uh, your previous states S1, S2, up to ST, and you want to predict ST plus 1, the behavioral environment, the only thing that you would need if your state is Markov would be the previous state, and you wouldn't need the previous states. So this is the definition of a Markov state. Uh, okay. Then next definition that we are going to have is the state transition probability. State transition probability is going to be probability of going, the probability of going to a state S prime when you are in state S. So given that you are in state ST, what's the probability of going to state ST plus 1? Or given that you are in state S, what is the probability of going to state S prime? This is called the state transition probability. So it defines for you the probability of going from one state to another state, and it can be, depicted as a matrix, where in each row of the matrix you you define all of the probability of for going from one state to all of the other states. So the first row here, uh, this row, the first one is going, the probability is the probability of going from state 1 to state 1 again. The second one is the probability of going from state 1 to state 2. The third one is the probability of going to state from state 1 to state 3. And the last one is going to be the probability of going from state 1 to state n if you are in state 1. So these are the probabilities, and we can show these probabilities as a graph too. So the first one is P11 is the probability of going from state 1 again back to state 1. The second one is the probability of going from state 1, P12, to state 2, and so on and so forth. And because all of these are probabilities, some of the values in each row should be 1. So P11 plus P12, if you add all of these together, uh, it should sum up to 1. So the sum of our values here, P1I should be equal to 1, because they are probability distributions. And based on what we talked about, we can define Markov processes. Markov process is a memoryless random process, or in other words, a sequence of random states that have Markov property. So formally, a Markov process or a Markov chain is a tuple. The first element of tuple are your states, a finite set of states, and the second one uh, is the transition probability, as we defined in the previous slide. And the second one gives you the probability of going from all of the states to all of the other states. Here we have a toy example. Uh, let's say that we have only three classes. So we have states classes, and we have the state pass, where you pass all of the classes. We have a Facebook state where you can go to the Facebook, and we have a pub state. Let's say that it is not pub. So let's say that it is a restaurant. So we have a restaurant state for the sake of our cultures. So we have all of these states, and we have the transition probabilities between these states. So the probability of going from class 1 to class 2 is 0.5. The probability of going from class 2 to class 3 is 0.8, and so on. So uh, we have the transition probabilities between all of these states. And if we have not shown the transition, so we do not have a transition between, let's say, class 1 and state sleep. In that case, the transition probability is 0. So all of the transitions that have 0 probability have not shown here. Okay, so this is a toy example, and we are going to use a lot this example for explaining different ideas. Um, you can sample different episodes from your Minecraft decision processes from this MDP. So uh, an episode is a chain of states that start from an initial state, and goes to a terminal state. So here are some samples. So sample episodes. The first one is class one, class two. Let's say that you class one, you go to class three, then you pass, and you go to sleep, and you don't have to study forever. The next one, class one, you go to Facebook. You again go to stay in Facebook. From Facebook, you get back to class one, then class two, and you don't have enough energy because you have spent a lot of time in Facebook. So you go to sleep. And we have we can have much longer episodes. That this one starts from class one. Facebook, class one, class two, class three, then you go to restaurant, then you go to class one, back to class one, again, Facebooks, a lot of Facebooks, class one, class two, class three, again, you go to the restaurant, uh, you get back to class two, you are exhausted from all of the states that you have been in, and then you go to sleep. So you can sample different episodes from these MDPs. And usually we can illustrate an MDP by a transition matrix. So a Markov chain, here you see a Markov process here. So this is a Markov process, and you can show it by a transition matrix. For example, the transition probability between C1 and C2, class 1 and class 2, is 0.5, and all of the values that have not shown here are 0. So you have 0 here, 0 here, 0 here, then 0 here, and 0 here. And so all of the empty space, all of them are zeros. So this is a Markov chain or Markov process. Uh, okay, this was all that I was going to talk about in this session. We are going to continue our discussion in the next session.